What we want to talk about today is graphs of trig functions. The algebraic approach to figuring out what a graph of a function of a single variable looks like is to maybe get a sense of the shape by plotting some points. And we certainly have some points that we can plot for the sine function, for instance, from our study of the special triangles and then general angles the last couple lectures. So let's go at the trig function as a function of the angle. We'll measure the angle in radians and write down x as the angle measure in radians, and then y, the function value, will be the value of the trig function. Let's do the sine function first and recall some of those values. When x is 0, the angle is 0. That is a horizontal line for a reference triangle. That limiting case gives a height 0, the value of the side opposite that 0, so the sine of 0 is 0. A 30-degree angle in a 30, 60, 90 triangle, we saw the sine could be the ratio of labeling it 2, 1, square root of 3, side opposite 1, hypotenuse 2, so opposite over hypotenuse for a 30-degree angle is 1/2. For a 60-degree angle, then the long side is the side opposite, root 3. So root 3 over 2, and that's standard labeled reference triangle. Pi over 2, a 90-degree angle, it points straight up. The y-coordinate is 1. 5 pi over 6, so we're going around 5/6 of the way. The reference angle would be the 30-degree angle aimed down towards the negative x-axis, but the height is still 1/2. All the way around 180 degrees, pi radians, the height is 0. It's aimed straight out the negative x-axis. 3 pi over 2 is 270 degrees back down the negative y-axis, and that makes the y-coordinate -1. 2 pi all the way around, the value would be 0. Let's plot these points. 1, 2, 3, 4, 5, 6, 7, 8 points. Let's put them on a graph, and we'll keep track of what's coming afterwards by looking at the values that arise. So we've got pi over 6. We did it at pi over 3 as another point. Pi over 2 at pi, 3 pi over 2, and 2 pi. And in between those, the values that the sine function takes on gives you the rest of that blue graph. That's the graph of the sine function. So what can you conclude about it just by thinking about how the values go? The sine function has as its domain the set of all real numbers. You can take the sine of any angle. The range has to be a number that could be a y-coordinate of a point on the unit circle. That's a number from -1 to 1. The sine function has symmetry associated with it. It's an odd function, symmetric with respect to the origin. What that means is that you go to the right and up to get a sine value, for example, and you would go to the left and down. Change the sign if you change the sign of the function value if you change the sign of what you're applying it to. Change the sign of the x, makes the change happen also to the sign of the y value, the function value. Periodic, as you wrap around the circle over and over, you go through the same values over and over. Periodic with period 2 pi. And you can list where the x-intercepts are, where that graph crosses the x-axis, and it crosses the x-axis at multiples of pi radians. It crosses the y-axis just once, where it goes through the origin. One more. The largest value that the sine function takes on is 1. That happens at pi over 2 and multiples of 2 pi added to pi over 2. So pi over 2 minus 2 pi, pi over 2 plus 2 pi, plus 2 pi again, so plus 4 pi, minus 2 pi again, so minus 4 pi added to pi over 2, and that set of periodic values are where the maximum happens. The very smallest it ever is -1, and that happens at these multiples of minus pi over 2, or minus pi over 2 with multiples of 2 pi added on. So let's look at this generic graph and calculate values of what a related function could be. So we're going to graph a function by a transformation. If you know what the graph of sine of x looks like, x minus pi over 4 has the effect of algebraically a horizontal shift. Minus 2 changes the scale of the vertical axis, so we can do those things in sequence. Let's start with, so we want to graph minus 2 sine of x minus pi over 4. Let's start with a base graph sine of x with some anchor points listed so that we can keep track of what's going on. And first of all, we'll multiply through by the minus 2. What's the effect of minus 2? Minus 2 times sine of x changes the orientation. Instead of starting out and going upwards, it starts and goes downwards. Instead of going up, it goes down. And the scale is times 2, so 2 units down instead of 1. So let's go back. 1 unit up, 2 units down. Sine of x minus 2 times the sine of x. So we're keeping track of that change that way. And now let's do the shift horizontally. X minus pi over 4 has the effect of moving the graph pi over 4 units to the right. So instead of starting at 0, we'll move it over pi over 4 units to the right. Instead of 0, pi over 4 units to the right. And all the points are dragged along by that, get shifted by that same amount, and that's what the graph of that scaled and shifted sine graph looks like. Okay, let's do the same trick for the cosine function. Again, we know about the cosine function values from the reference triangles that we could use, 30, 60, 90 triangles in different quadrants, and we can use that to read off values of the cosine function. Remember, the cosine function would be the x-coordinate of a point on the unit circle, so that if you've got an angle of 0 radians, that's pointing straight out in the horizontal direction, the positive x-axis. On the unit circle, that goes out 1 unit. So 1 for the value of cosine of 0 radians. Pi over 6 is the 30-degree angle. The cosine would be the side adjacent to that over the hypotenuse. If you label the 30, 60, 90 triangle with the standard labeling 2 for the hypotenuse, 1 for the short side, and √3 for the long side, then opposite over or adjacent over hypotenuse would be √3 over 2 as cosine of pi over 6. For a 60-degree angle, pi over 3 radians, it drops to 1 over 2 for the ratio adjacent to hypotenuse. Pi over 2, the limiting case is 0 for the x-coordinate. If it's aiming straight up the y-axis, then the x-coordinate is 0. 2 pi over 3, we're going in an x-axis. It's negative for the x-coordinate in quadrant 2. So the cosine of 2 pi over 3 is minus 1/2. Pi is straight back along the negative x-axis, 1 unit back to hit the point on the unit circle. So cosine of pi is minus 1. 3 pi over 2 is aiming straight down the negative y-axis, and cosine would be 0 there. 2 pi, 1 full revolution, and it cycles back and has the same value at 2 pi that it had at 0. So we've got a set of points we could plot, and if we do that for the cosine function, we've got values that fit on a curve that looks kind of like the sine function curve in that it cycles through values. It gets from 0 to 2 pi and is ready to start again. We just need the x coordinates instead of the y coordinates, so the shape starts at 1 and ends at 1 when you've made a full revolution. We could do tangent as well. The graph of the tangent function you could approximate. You could sneak up on with some specific values. Let's get values around 0. Notice that the tangent is an odd function, so it makes the most sense to understand this table from the middle. At 0, the tangent is 0. At pi over 6, the tangent is, well, what would it be? Side opposite over side adjacent. In a 30, 60, 90 triangle labeled, opposite is 1, adjacent is root 3. So 1 over root 3 would be the same as root 3 over 3, and here's a decimal approximation. That's what it is for the positive angle. The negative angle gives the negative value of that. So we've got these two kind of coupled. At pi over 4, 45 degrees, in the isosceles right triangle, the side opposite and side adjacent match. So the ratio is 1. And the negative angle, it would be minus 1. For pi over 3, instead of 1 over root 3, it would be root 3 over 1. For opposite over adjacent, draw the 30, 60, 90 triangle and look at it to make sure. So we've got a value for root 3 and for minus root 3 for the angle minus pi over 3. And a numerical approximation of that, minus 1.73. So there is what those points look like plotted. Now it's worth using the periodicity of the tangent function to do this over and over, and also to note that we've stopped in the graph at the last points that we plotted. That was pi over 3, but at pi over 2, the value of the tangent's undefined. The reason is that the value gets arbitrarily large. So we could show that by showing the periodicity and that by scaling this picture so that we've got more points that we're showing and more than one period that we're showing. So these vertical asymptotes at minus pi over 2, 3 pi over 2, up and down, are places where the tangent function's periodicity kicks in. And if you get the graph of the tangent function from minus pi over 2 to pi over 2, you can use the central portion and repeat it over and over again, exploit the periodicity of the tangent function to get what the graph looks like on this bigger domain. What do we know about the tangent function? Its domain is all real numbers, except you want to make sure that the ratio that defines the tangent function makes sense. That's when, if we've got pi over 2 or an odd multiple of pi over 2, that would be a situation where the side adjacent would be 0 in the reference angle, and division by 0 would exclude those angles from the domain of the tangent function. Any number can arise as a ratio. The range is all real numbers. The tangent function is an odd function. That means that if you go to the left and to the right and up, you would go to the left and down, to the right and up. A corresponding point on the graph reflects to the left and down. So that is the symmetry of the graph that this indicates. It's a periodic function. Remember that the period of the tangent function is only pi, not 2 pi as it is for sine or cosine, because the arithmetic of signed numbers for the tangent function means that it's duplicating values as positive over positive in quadrant 1 and negative over negative in quadrant 3. So you only have to go halfway around from quadrant 1 to quadrant 3 to get the same ratios. The x-intercepts are the places where the graph crosses the x-axis, all the multiples of pi, and it only crosses the y-axis once at the origin. Here are the x-intercepts, all the multiples of pi: 0, pi, 2 pi, minus 2 pi backwards and forwards. and the graph only crosses the y-axis once at the origin. Any function, if you think about it, will have at most one y-intercept, because if it had more than one y-intercept, that would be two y values that go with the same x value, and that couldn't happen for the graph of a function. And the last thing to notice is where those vertical asymptotes happened. They happened at pi over 2 and pi over 2 with multiples of pi added on. Well, we've spent most of the time and most of the emphasis is on the sine, cosine, tangent functions. It's probably worth thinking about what the cofunctions look like, but don't do it by memorizing a graph. Do it by thinking about what properties you would expect the graph of the reciprocals to have. Here we've got the graph of the sine function. The sine function is the red curve in the middle of this. If you think about the reciprocal identity, the cosecant is the reciprocal of the sine function. So the cosecant function is a graph whose characteristics are determined by the graph of this red function. In particular, everywhere the red function is 1, the blue function is the reciprocal of 1, so it's also 1. Everywhere the red function is minus 1, the blue function is minus 1, so that matches. Everywhere the red function is 0, the blue function is defined as a ratio that would have a 0 in the denominator. So it's undefined for those values. All these places where the sine function takes on a 0 value, the cosine or the cosecant function, the reciprocal function, has a vertical asymptote. So this is a graph to link the graph of the sine function to the graph of the cosecant function. If you'd like, you could link the graph of the cosine function to the graph of the secant function in just the same way. But I'll leave that for you. How about that? Okay, that's it.